All right, everybody, here we go. I didn't want to leave you without one more example here. So we are going to do locomotive and two cars. We're going to derive the model in state space and create a Simulink model. So let's get started. Hopefully y'all can see this. So what exactly are we going to be doing, right? So first off, here's our system. Right? I've got mass 1. We'll call this the locomotive. There's a force pulling it, an applied force to the left. Notice Z1 describes the motion of M1. There's a spring and a damper connecting M1 to M2. This will be car 1. And finally, we have car 3. Again, spring and a damper. And notice we've got rolling friction as given by the equation B sub R Z I, Z dot I. Okay? Each one of these has their own position. We want to derive the model using SSR. And we're told in the problem statement, which I didn't give you, but we're told that we want to measure Z1 minus Z2, so the displacement, the relative displacement of these two, and the velocity of this car. Okay? Now, why is that significant, right? Why is that significant? Why is that significant? Because when we're told to measure something in SSR, that means we want to use this as Y1 and Y2. Okay. So we're going to start the same way we always start here, right? And we are going to get our free body diagram going, right? Get our free body diagram game on here. So we start with mass 1. You can see my beautifully defined mass 1 free body diagram. I've got the applied force, I've got my motion positive to the left, and I've got my spring and my damping pointed to the right, and my rolling friction also pointed to the right. Interesting. Why is this interesting? Because this assumes that Z1 is greater than Z2. Right? So the way that I've run this is I'm assuming that Z1 is greater than Z2, and I've assumed that Z2 is greater than Z3. That is what I, in fact, have assumed here, and you can see my free body diagrams here. Notice equal and opposite, right? These are internal forces connecting these two cars, and likely they will look the same way on the next one, right? So here's mass 3, car 2. You can see it labeled, right? Fantastic. Right, so there's the free body diagrams. Inputs. We're going to go down the chain, right? I've got FAT, applied force as a function of time. I've got Z2 and Z3. Okay. Output. Well, the output from here, right, is Z1. I'm sorry, that should be Z1 right there. My bad. Z1, Z2. This is Z2, and this is Z3. Okay. So, applied force and Z1 are the outputs, input and output combination for this block diagram. I put in this applied force, I get some motion, right? This motion then controls the motion coming out of here. And this motion, Z2, controls the motion coming out of here. We need our truths. Some of our truths are common. Sum of the forces is equal to mass times z double dot, right? In this case, we've got Fk, right? And I'm going to call the connection between the locomotive and car 1 Fk1. And Fk1 is equal to k times z1 minus z2. Okay? Fk2 is equal to k times z2 minus z3, right? This is the connection between car 1 and car 2, or I'm sorry, the locomotive and car 1, mass 1 and mass 2, and this is mass 2 to mass 3. We've also got FBR, which is given, right? That was the rolling friction coefficient times z dot of the block that it was applied to. And I can come up with FB1, which should be B1, or not B1, but just B times Z dot 1 minus Z dot 2, and FB2, which is B times Z dot 2 minus Z dot 3. Fantastic. We are rolling here, right? And so those are my truths. Those are my truths, right? And those are going to be important for us. Those are going to be really important for us in a minute. But before we get there, well, I guess we're getting there now. We'll do our reduction. Right, so we're going to reduce this. How do we reduce these data, right? How do we reduce these data? Well, let's start with mass 1, or the locomotive, right? We start with mass 1, or the locomotive, as it is called. What do we get? Well, we'll get m1z double dot 1 is equal to the applied force minus the rolling friction on block 1 minus the damping and the spring forces, minus the damping and the spring forces of our in between car block 1 and block 2, the locomotive and car 1. Fantastic. Put this back up like that. Great. So let's continue, right? We'll plug some things in. Well, this should be FBR. What FBR is just BRZ dot 1 minus B times Z dot 1 minus Z dot 2 minus K times Z1 minus Z2, right? And now this is cool, right? Because I can algebra this. I'm going to get all my Z1s on one side and leave everything else on the other side. So I'll get M1Z double dot 1 plus BR plus B Z dot 1 plus K times Z1 is equal to FA of T plus B Z dot 2 plus K Z2, right? And we'll save this guy right here. Equation 1. So equation 1 is M1Z double dot 1 plus quantity BR plus B Z dot 1 plus KZ1 is equal to F sub A of T plus B Z dot 2 plus KZ2. Okay, Dr. D. I'm picking up what you're putting down here. Whoa. things are falling all over the place, guys. Things are falling all over the place. Let's get ourselves a little more room here. Perfect. All right. So let's talk about mass 2, or car 1, as we have called it. Right? Okay. So if we're talking about M2, well, let's start there. M2 Z double dot 2 is equal to FK1 plus FB1 minus FBR2 minus FK2 minus FB2, right? So there's a lot going on block 2, but that's because it's free on both sides, right? Free ends on both sides. Dogs and cats living together. Complete chaos. All right, so we're in algebra. And this one is going to be the messiest of all of the equations. Sorry, that should be a minus right here. My mistake. Okay, so, because you can't read my chicken scratch. M2 Z double dot 2 is equal to K, quantity, Z1 minus Z2, plus B, quantity, Z dot 1, minus Z dot 2, minus BR, Z dot 2, minus K, quantity, Z2 minus Z3, minus B, quantity, Z dot 2, minus Z dot 3. That's what we're looking at. And I will put this in my input-output format. Again, we're going to take this equation right here. Call this 2. What does it say? In case you can't read it, in case you're having trouble reading this, M2Z double dot 2 plus quantity 2B plus BR Z dot 2 plus 2K Z2 equals B Z dot 1 plus KZ1 plus KZ3 plus B Z dot 3. Okay, so that's what we're looking at here. That's what we're looking at here. Right, and then for mass 3 or car 2, this one's not too bad, right? This one should be pretty nice for us because we'll have M3Z double dot 3 is equal to FK2 plus FB2 minus FBR3. M3Z double dot 3 is equal to K times Z2 minus Z3 plus B times Z dot 2 minus Z dot 3 minus BR Z dot 3. Fantastic, fantastic. So we will algebra M3 Z double dot 3 plus B plus BR, quantity, Z dot 3 plus K Z 3 equals B Z dot 2 plus K Z 2. Again, M3Z double dot 3 plus the quantity B plus BR Z dot 3 plus KZ3 is equal to B Z dot 2 plus KZ2, right? And again, we'll take this over here and we'll do that guy. Question, right? So that you guys can see it though, first off, right? That equation down there, 3. Question for y'all. What order system is this? Put it in the comments. Put it in the comments. So we've gotten our 3 equations. Let's just take a look at them one more time. All right. Oh, trying to get that on there. Right. We've got equation 1, equation 2, and equation 3. All right. So now that we have our input-output equations, we are going to want to do our state space. All right. So if I want to get state space, right? State space representation. How do I do it? How do I do it? Well, first I need to know n. What is n? N is the order of my system, right? So hopefully you already answered and you're not going to cheat and then put this answer into the comments. But hey, n is equal to 6, right? 6th order system. How do I know that? I have 3 second order coupled differential equations that describe this system. That's how I know that. So now, if n is 6, I need 6 state variables, right? So let's do that. x1, x2, x3, x4, x5, x6. I've given myself just barely enough room, right? So I've got z1, z.1, z2, z.2, z3, z.3. But remember, I also need the derivative of these. Why do I need the derivatives? Well, we'll talk about that in a second, but it has to do with the condition. Sorry, this should be a single dot. With the condition that we are trying to fulfill in making these equations. Right, we need x dot as a function. We need x dot as a function. Right, so remember what we're looking for here is we're looking for x dot as a function of either x, of some combination of my state variables and u. Right, that's what in fact we are looking for. And something interesting and nice happens here, right? You can see that we're going to get a couple of equations here, right? That pop out, things that are equal. And we'll talk about that in a second. So one of the biggest questions that I get in class, is, Dr. D, how am I supposed to know which state variables to choose? And the fact of the matter is that there's no unique choice of state variable. You can choose whatever you like. However, my general rule of thumb for students and for those who are just starting out in state space representations is to think about how energy is stored in this system. And then choose your energy storage variables. Now, this is a mechanical system, a translational mechanical system at that, and therefore it will store energy in one of 2 ways. It will either store it as kinetic or potential energy. Kinetic energy is a function of velocities. Potential energy is a function of position. And that's why I chose these state variables. There's also a couple of other things that we have to cover, right? Well, that we should cover while we're here. Right? So let me say, this is the condition that we're trying to fulfill, and we'll see what I mean by that in a second. But U, my input, is my force, and we were told what to measure. We were told that Y1 has to be equal to Z1 minus Z2, okay, and Y2 was equal to Z dot 1. Now, what do we do with that? Well, I'm going to take a look at here. I'm going to say, well, Z1 is X1. So this is just X1 minus X3. And this actually equals X2. And I know that that's hard to see, and I apologize. I'll try to write bigger as we continue forward. So what do we do with this now that we have this, right? Now that we have those and we have our equations, what we're going to do is we're going to solve our equations for the highest order differential that we have. And we want one equation for each of our variables. We want one for x dot 1, one for x dot 2, x dot 3, x dot 4, all the way down to x dot 6. So let's start here, right? We'll start with x dot 1 is equal to x2. Dr. D, you're crazy. I know, but not about this. Okay? X dot 1 is equal to x2. This fulfills this condition. X dot is a function of either x or u. Okay? This is a function of x. Okay, now if we rearrange equation 1, let's take a look at it again, just to refresh our memory, right? But if I rearrange equation 1 and I plug in my state variables, so that's this equation right here, m1 z double dot 1 plus br plus b times z dot 1 plus kz1 is equal to fat plus bz dot 2 plus kz2. So I'm going to rearrange this. I am going to solve this equation for z double dot 1. And once I do that, I will rearrange it and I will plug in my values. And what I will get is x dot 2, right? Because x dot 2 is just z double dot, right? You can see it kind of right here. And that's going to be equal to negative quantity BR minus B over M1 times X2 minus K over M X1 plus B over M1. These are all M1s. I apologize. X4 plus K over M1 X3 plus 1 over M1 times U. Now, if I had done myself any favors here, I would rearrange these to be as X1, X2, X3, X4 in order. But it doesn't really matter. But you'll see why it's nice to have that later. All right, X dot 3. But X dot 3 is just equal to X4 for the same reason that X dot 1 is equal to X2. X4. This one's going to be a little bit longer, and I'm going to try to keep this one in the correct, well, not the correct order, but in order of my state variable. So K over M2 X1 plus B over M2 X2 minus 2 times K over M2 X3 minus 2B minus BR over M2 X4 plus K over M2 X5 plus B over M2 X6. Now, Dr. D, where did this come from? Great question. Great question. we took this equation, right? Oh, I'll get there. Right here. We took this equation and we solved it for z double dot 2, and then we plugged in the state variables. Right, and then we plugged in the state variables. Okay. X dot 5 is equal to x6. Another slam dunk. And then we've got x dot 6, and I know you can't see it because of the angle. You'll see it in a second. It's x dot 6 is equal to negative b plus b sub r over m3 x6 minus k over m3 x5 plus b over m3 x4 plus k over m3 x3. Okay. All right, so let's see. Now we can see them. We've got 6 equations. These all fulfill this, right? These all fulfill this. Now, there's 2 things that we need when we're talking about state space representations, right? If we want a complete state space representation, we are trying to create these 2 equations. Right? I'm trying to create these 2 equations. So we're going to start here. This is my state equation, and this is my output equation. We're going to start with the state equation. X dot equal ax plus b times u. And really all I'm going to do, instead of doing the whole thing out, is I'm going to populate these matrices, right? So let's start with the A matrix. Okay, so where does the A matrix come from? Well, I'm going to take all these, right? So remember, let's go back here. Well, remember, this is going to be x dot 1, x dot 2, x dot 3, x dot 6, right? That's what the x dot vector is, times some matrix that I will call my A matrix, times my x vector, right, plus some matrix that I'm going to call my B matrix, times my vector of u's, but in this case I only have one u, right? So this is what we're trying to take from our equations, right? Which equations? These equations. I'm going to turn these equations into, right? So look, if I were to draw the brackets around here, that would just be my x dot, right? And the rest of these are linear combinations here. So let's see what I'm talking about, right? So if I'm going to do my first row, the first row of my A matrix, these are the things that are going to get multiplied. Hold on. I want to show you. I'm going to do the first row of my A matrix here. So this is my x dot 1 equation. I have an equation for x dot 1. X dot 1 is equal to x2. Right? X dot 1 is equal to x2. So we end up with 0, 1, so 1, 2, 3, 4, 5, 6. Because this is going to tell me 0 times x1 plus 1 times x2 plus 0 plus 0 plus 0 plus 0, right? And that's my A matrix. Likewise, I can do the same thing for all the other lines, right? So, okay, so let's grab my x1, because all my x1 terms will be in this first column. So x1, negative k over m, negative k over m1. x1, well, there's no x1 in this equation. x1, this is k over m2. There's no x1 in this equation. And there's no x1 in this equation. So again, no x1, no x1, yes x1, no x1, yes x1, no x1, no x1. So it should be 0, negative k over m1, 0, k over m2, 0, 0. 0, negative k over m1, 0, k over m2, 0, 0. Okay. And so, look, just so we can keep these straight, right, those are my x1 terms, right? So let's grab my x2s. Here, here, there's a 0 there, here, 0, 0. So it should be 1, negative b, right? Negative br minus b over m1, 0, b over m2, 0, 0. And in fact, and I apologize that these aren't going to line up perfectly, but that's how the cookie crumbles, guys. I apologize. All right, so there we are. Let's get the next one. We're going to get all of our K3, our X3s, right? So, all right, 0, then K over M1, 0, negative 2K over M2, 0, K over M3. And again, boom, boom, right? And boom. The rest are zeros. Let's do the fourth, right? Let's do our X4s. Boom, 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 boom. 0. So 0, something, 1, something, 0, something. B over M1, 1. Negative 2, B plus BR over M2, 0, B over M3. And so this is where it's going to kind of take a turn here. I'm going to try to mark these off the best I can, guys. I apologize. All right, what about my X5s? All right, what about my X5s? What about them? Right, 0, 0, 0, 0. Right, so I'm only going to have about 2 entries for this. It's going to be 0, 0, 0. 0, 0, 0. K over M2, 0, negative K over M3. And then my final entry, we'll go back to this color, is going to be my X6s. And my X6s should be 0, 0, 0, 0, 0, 0, B over M2, 1, negative B plus BR over M3. And this whole thing is A. All right, so let's see. So everybody can see the whole thing. No, just kidding. There we go. That's what A looks like, right? So we are expecting it to be a 6x6, and it is a 6x6. I apologize that it looks like hot garbage, but so it is, right? Where does that come from? It comes from here, right? All the x1 terms are my first column. If I don't have an x1 term for that equation, it gets a 0. Okay. We also need B. We need our B matrix, right? Also need A. Okay. So I want you to see this. So here's B. How do we find B? Well, B, remember, B is all the things that multiply U. B is all the things that multiply U. Okay. Well, if B is all the things that multiply U, I only have this in my... So this is... Are you telling me, Dr. D, this is all zeros except for that one entry? You bet your bottom dollar that's what I'm telling you. 0, 1 over M1. 0, 0, 1, 2, 3, 4, 5, 6. That's that. We can talk about the y equation, right? We wrote it down earlier, but y was equal to x1 minus x3, and y2 was equal to x2. Okay, remember the equation we're trying to fulfill. Right, this one's going to be a little smaller, so I'll write this out. y1, y2. You know what? We're going to do it on this. We'll do it on the back side. y1, y2 is equal to something times my x matrix, right? x1, x2, x3, x4, x5. I apologize, not my x matrix, but my x vector. And I didn't give myself enough room here. So we'll call this C. Plus D times U. Okay. So remember, if we're looking at this equation, right, I want to make C, right, this is x1, so all of my first column should be my x1. I got an x1 here. That's 1, 0. So C should equal 1, 0. Right, okay. x2, 0, 1. 0, 1. x3, well, that's a negative 1. Negative 1, 0, and then x1, x2, x3, x4, x5, x6, x4, x5, x6. D, well, it's just going to be zeros, right? There's no U's. There's no U's in there. Not 8, but 0. 2 zeros. Right? And that's what we're looking at. And that's what we're looking at. Okay, so I apologize for the sloppy cut, but we've got Simulink up. How do I get Simulink up? I open MATLAB and I type Simulink. And rather than having you guys watch my Simulink load, I just cut it. Okay, so what are we going to do here? We want to build a Simulink model. Right, we want to build a Simulink model. So here we go for our Simulink model. Right. Not only that, but as advertised, we want to build a state space block representation. So I'm going to type, we'll click in my workspace, I'm going to type state space. Before I even get there, it'll bring up my block and I will double click it. And it's going to ask me for A, B, C, and D. Well, we found A, B, C, and D, right? And this is where we can do a couple of things, right? So I'm actually going to say that this is A, this is B, this is C, and this is D. And I'm going to say okay, and it's going to yell at me, right? It's not going to like that. So I pull up MATLAB, and I'm actually going to define my matrices here. So I'm going to make A row 1, call it AR1, is equal to 0, 1, 0, 0, 0, 0. Okay. So I'm not defining any of my variables yet, right? I'm going to do that in a second. So I've got the first three rows. Unrecognized variable, okay. Okay. Well, that's a problem, right? So let's just put in some placeholder values. K, we'll say is 10,000. That's going to be Newton per meter. Right. Okay. B, we'll say B is going to be 100, and that should be Newton second per meter. Okay. BR equal to 250. Second per meter. M1 300,000 kilogram. M2 150 and M3 100,000. I think that's everything, right? I've got K, BR, B, M1, M2, and M3. That should give me everything. So now when I come back up and I run this, I should get a R1, A2, AR3, AR. Right, so let's keep going. AR4 is equal, well, that's the fourth row. 1, 2, 3, 4. That's going to be K over M2, B over M2, negative 2 times K over M2, negative 2 times B plus BR divided by M2, K over M2, B over M2. AR5. And AR6. So Dr. D, why are we doing this? Seems foolish. You'll see. And we forgot an equal sign, which is fine, easy to fix. Boom. So now A is equal to, wait for it, AR1, AR2, AR3, AR4, AR5, AR6. So the semicolon will tell it that I want a different row. And I can show the whole thing. And there it is. There's my matrix, A. Instead of B, right, B is going to be equal to 0, 1 over M1, 1, 2, oops, sorry, 0, 0, 0, 0. That's B. C is equal to 1, 1, 0, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. D equals 0, semicolon 0. Remember, semicolon tells it that that's the end of a line in a row or a matrix. So now, when I come back into my Simulink and I hit my button there, it will fix this. It refreshes it. And I have an A, B, C, D. I'm going to set my initial condition to 0. We didn't say what F was, right? F of a T, right? My applied force. But I'm going to need a source. So open up my libraries. I open up my libraries, and I'm going to come down to sources, and I'm going to grab a step function. And I'll drag it on out over here, put it there. There's my step function. All right, so my step time, we'll say, 5 seconds, it turns on, initial value of 0, and we'll say we're going to apply 600,000 newtons. Okay, and I need something to read it out, so we'll just put a general scope there with a single input port, right? Do that. Well, actually, that's not going to work, right? We need to demux this. This will come in there. So why did we demux it? What does that buy us? Demuxing takes it from an array, right? And I'll make this larger so we can actually see what's going on here. That's just a step. So mux, demux, right there. And mux just looks like a black bar. Okay, cool. I'm going to come in here. I'm going to press Control E. Control E brings up my parameters, and I'm going to change this to 1e-4. Hit apply, go OK. All right, I'll set my time to 20 seconds. I'll open up my scope. All right, what I want to do first is come over to View, Layout. I'm going to pick 2 like this. Before I do that, I will set this to be displacement, and I'll spell it correctly. Displacement velocity, right? Come back, hit play. And here we are. For a step input, and we didn't hit 20 seconds, wasn't long enough. So let's put it at 60 seconds by changing our time step right here. We'll bring our scope back up and I'll hit play for 60 seconds. Notice the displacement continuously shifts in 1 minute. And it shifts between 0 to 50. That's in meters, right? So this is significant. We've probably broken this. Okay, will this ever reach a steady state? Because this looks like it continuously shakes up and up and up. Good question. Let's see what it looks like in 600 seconds. Now this is going to take a second. All right. So our peak continuously rises and rises. All right. It looks like we are gonna settle out though. So we have a lot of oscillatory behavior going on here. And once this finishes running, we should hopefully see that our force, right? We should hopefully see that our velocity will have settled out. But we're going to have to wait and see. All right, so there's 600 seconds. And it doesn't really. Does that make sense? Sure, right? I'm pulling with a continuous force, right? So this should peter out eventually, but it's such a large force that it's going to take a lot of time. Finally, I can delete this. Now, what if I wanted a sine wave? Right? I put in sine, not that guy, sorry. Type sine, I grab sine wave. There it is. Wire that up to there. Now instead of 6, we'll drop it back down. Drop back down to a minute, and we will run it again. Now this was a unit sine wave, but that's funky, man. That's funky. So what in the heck is going on? Now another thing that we can do, if we come back into here, right? Remember, I set all these components, right? I set all these variables. So I can change M1, and I can say, well, what happens if M1, what if all the masses are the same? Right, what if all the masses are the same? How does that affect my output? What else could I do? Well, let's do that first. All right, let's take a look at that first. So here's my output. I can run this again. Does that look any different? Certainly changed it somewhat. Okay. What if I change my ruling, or what if I change B? Right, B was equal to 100. What if I make this 500? What if I increase the damping by 5 times? Take a look, right? You see my response here? I've increased the damping by 5 times. What did I do? Doesn't look like it did much, does it? All right. What if I wanted to do more than a unit here? What if I change my frequency to 60 radians per second and I have an amplitude of 10? All right, last one. Now that's running at 60 radians per second with an amplitude of 10. And that's a very small amount of displacement, right? That's 10 to the negative 6th. It's a very small amount of displacement. But check this out. This velocity is really shaking. It's really vibrating. Anyway, that's how you create a Simulink model using a state space representation. If you liked the video, hit like. If you didn't like it, hit dislike. You know what? In the comments, let me know what you think. Let me know if these results make sense. And let me know if you tried this and it worked out for you. Until next time, guys, take it easy.